Okay, as I said, my name is Søren, and I'm from Aalborg University, and I will talk about how we have extended the software transactional memory implementation of Clojure with support for side effects and transaction control. First, our reasoning for working with Clojure and extending its software transaction memory concepts are that we have a huge problem with multi-core processors nowadays. We have more or less the only option of buying a new processor is that it contains multiple cores, and we have to somehow develop programs that support this without running into problems such as deadlocks, side effects, and in general non-deterministic behavior that might first be present in our programs when we have shipped it or when we run it 5 years afterwards. And our contribution to solve this problem is that we have taken Clojure's implementation of software transaction memory, which I will go into detail later, and extended it so it can synchronize forms that contain that, when executed, perform some sort of side effect. And we have enabled developers to directly control transactions created by Clojure's software transaction memory system. And using that, we can use the system to not only synchronize data as currently what it's used for, but also synchronize threads and perform other operations. And if anybody wants to try using the implementation, we gave it a very novel name, eClojure, standing for Extended Clojure, and it is available on my GitHub repository together with a full set of unit tests for the current implementation in addition to Clojure's existing unit test system. And why Clojure? First, it runs on top of both two existing platforms, the JVM and the Common Language Runtime, which, especially for industry, is a huge bonus since you can utilize your existing libraries and interfacing them with your Lisp code. So all your existing work can still be utilized. And as a functional language, it utilizes immutable data structures as a default, which is a great thing when we are working in concurrent systems, as we can now share data between threads without having to do any form of synchronization, as reading is always synchronized by default, or what you want to call it. It's not a problem if multiple threads reads the same data. We first have a problem if you start writing to it. And if that becomes a necessity, then Clojure, instead of locking, provides software transaction memory, as I've hinted at multiple times, and we can use that to synchronize access to our data. And in more detail, software transaction memory, most are probably familiar with the locking concept, where we lock access to a variable, so only one thread can mutate it at the same time. That has some problems, primarily locking order. You have to take care you don't cause deadlocks by taking locks in different orders, etc. Software transaction memory removes this problem by you taking an optimistic approach. We try executing a set of expressions, and if that is acceptable and we don't have any conflicting operations with another transaction, we allow the transaction to commit, and everything is fine. Of course, this hints at the problem with side effects, as if the transaction conflicts, then it has to roll back and execute again, which for a side effect is something we would like not to happen. In Clojure, this concept of software transaction memory is implemented using multi-version concurrency control, where you have a snapshot of all mutable states in the transaction when you start the transaction. This has some nice properties, mainly that we can now read and write concurrently in two transactions, and we only conflict and have to roll a transaction back if we have multiple writes. Unfortunately, this also can lead to the problem of write skew, where you really want to read the same value, so another transaction writing to it is unacceptable, but Clojure contains systems that can prevent that. Well, so for a small example, we have a vector of numbers, and in order for it to be used as a mutable value in a software transaction memory, we have to store it in the type ref. And ref is simply a type that contains the value and the metadata necessary for the software transaction memory implementation. And we can then create a transaction using dosync, which transactions, and we use the function also that takes a ref as its first argument and a function as a second argument. And the function transforms the value inside the ref, and the result of that function is written to the ref in the end. So that's more or less the quick overview of how that works in practice in Clojure. However, it has some problems as we will do. First, there's an example of where side effects becomes problematic. If we have an empty vector of where we want to store a set of keys, and we have a vector of data that we want to insert into a database and keep them organized in the same way. So the same order of the keys are present after we have executed all our inserts. This, however, is not possible at the moment, as if we insert a row into a database and then update our rows and keys vectors, the transaction might be forced to roll back, as it could conflict with another transaction doing the same operation. And if we do that, then the database operation can be executed again, and we have multiple instances of the same row in the database. So we'll have to stop that. Second, the Clojure provides absolutely no capabilities of controlling a transaction. You can start a transaction and let it run to the end. We can, if we allow developers to actually control these transactions, use them for other aspects of concurrency than just synchronizing data. Some of these capabilities can be emulated. In this case, we use the exception handling system in Clojure to exit a transaction and stop its execution. However, this is slightly is not as nice as it could be, and we need to, and it can only be utilized if we have already put the exception handling around the transaction before we started the transaction, and we need to have a separate exception to not conflict with actual error handling. So it's not as nice a solution as we would like. So in order to extend Clojure, the system, we started by adding support for event management in the Clojure runtime. This is due to most of the extensions we have added, especially for synchronizing side effects, utilize the notion of events. We want to execute code at a specific time during the transaction's lifetime. So we have a set of functions for adding events based on a keyword. We can delete events attached with the same keyword, and we can fire off an event somewhere else in the system and execute the handle we previously added to the event handler. And in order to allow data to be transferred from both where you define your handle and from where you execute notify, have we introduced the concepts of context. So when you create the listener, the handle, you can add parameters. So the function you add matches the number of parameters you add. So that is fairly obvious. But when as notify could be executed multiple places throughout the program and from different places, is the number of arguments cannot be determined when you attach your handle. So instead, we bundle all arguments and make them available inside the handle as the context. On top of this event management system, we have added a couple of events to the software transaction memory system in Clojure. So at 3 points during the execution of the transaction, we execute an event, and if any handlers are registered for that event, we run that handle. First, after commit is, as the name implies, executed after the transaction has committed. This does not specifically add any extra capabilities, but allows code to be easily sent to execution after the event after the transaction is finished, which in many cases is a fairly nice capability. The next we have is on abort, which if a transaction conflicts with another transaction and have to roll back, is executed. In this way, a developer can clean up whatever side effect has been executed and force the transaction to go back to the original state. This is not a perfect solution, as printing to the screen or sending a document over HTTP is not capable of being rolling back. But if you have mutated a data structure similar, could this be a possible solution? And last, we have on commit, which splits the committing of a transaction into 2 parts. You execute when we are ready to commit and we know we don't conflict, we take ownership of all refs that have been used in the transaction, so we can write to them without any problems. After that has happened, we execute on commit and allows a developer to to perform side effects and mutate refs that has already been used in the transaction without fear of them causing conflicts, as we already have taken ownership, and we commit the transaction fully. To help the developer take ownership of multiple refs, we have added a small macro log refs that takes a code that takes a form and extracts the refs that it contains and takes ownership of them so that they can be used in the on-commit. And the last two elements, JavaRef is useful since allowing side effects to be used allows existing Java APIs to be used. So we have to extend the ref type to support Java objects, as these are stored as references and not as directly as data, which the existing ref type expects in Clojure. Okay, the second set of extensions is inspired by Haskell's implementation of software transaction memory that already contains retry and Oils. The concept of retry allows synchronization of threads by if you have a transaction and you have read multiple refs throughout this transaction, you can then call retry and the transaction will be forced to restart and then block. The transaction will be unblocked again once one of these refs has been read or has been changed. This allows developers to operate on the notion of I have an invariance that does not hold for my transaction, I cannot continue. So since I call restart, and since you have just checked a ref using some sort of if statement or similar, you have read this ref, and calling retry will then block the transaction until this ref is changed. And since the invariance did not hold when you checked it, you can then have the assumption that when it is changed, then hopefully it will come to a different output. And then the difference between the two versions is that the original version using Haskell only blocks until one ref is changed, while Retry All waits until all refs are changed. So if you have multiple refs that must all be changed before it makes sense to unblock the thread, you can do that now. And additionally, you can specify explicitly what refs you want to wait on, another new feature, and you can wait on both on a set of refs, and once these refs are changed, you can execute a function, and depending on if that function returns true or false, you will unblock or continue to be blocked, allowing whatever invariance changes you want to do. The concept of Oils allows multiple functions to be combined, and if there is a conflict in your transaction while you execute the first function, you continue on to the next one. So even if the transaction could not execute the first set of instructions, maybe you have some way you can continue by executing another code path. And the difference between the two versions is that Oils only continues if you explicitly ask for it using retry, so you have complete control over when you continue to the next execution, to the next function, while retry all will continue using both retry or if there is a conflict with another transaction. And the reason for having both cases is that if you want control, you can use the not all version, or if you want to take into account that you might conflict and continue anyway, then you can use else or all. And as a solution for the small motivating example we showed in the start with ending a transaction, we have the single function terminate that simply ends a transaction without any other code needed. So a much cleaner solution than using exceptions and trying to put an end. For the implementation, the original implementation Clojure consists of 3 parts. The interface written in Clojure, added to the file core, that communicates with the ref type implemented in Java. And when our operation is called on the ref type, that ref type calls down to login transaction to Java that includes your Clojure's entire implementation of software transaction memory. There's one exception to this path of execution, as when you create a transaction, then that goes directly to the login transaction, but otherwise all operations go through the ref as they manipulate the refs themselves, and they then send it down to login transaction. For our extensions, we have added a couple of extra files and changed one. First, we needed an additional interface for the additions we have created. We added them in a separate file to not to change as little as possible with the original implementation. And likewise, eClojure calls to Java ref if you have a Java ref object or a Java ref type where you contain a Java object reference, and that calls to login transaction. So it follows a similar execution path to the existing implementation if you use the other ref type. For the implementation of for the synchronization of side effects, we added the event management system that is accessible both to login transaction, so it can execute events once the transaction has reached a specific step, and it is available from the Clojure interface, so a developer can use the capabilities of the event management system for their own programs if they have a need for executing events or in the program. And last, for the implementation of the transaction and control concepts, these could all be implemented by extending login transaction, as these are operations directly on the transaction. And to implement the behavior on how and when a transaction should block and unblock, where we implemented what we call SCM blocking behavior. And this class can be extended by inheritance and then simply implementing another behavior for when the transaction should unblock. And last, the conclusion. We created eClojure that extends software transaction memory in Clojure with support for synchronization of side effects and performing explicit transaction control. We have performed some initial evaluation, and it indicates that we are getting some usability enhancements at the cost of a slight constant overhead when we execute the transactions due to some extra instrumentation to support the transactional control features. However, this is still only our initial evaluation. And the overhead is something we anticipate can be reduced further, as our original implementation, as this implementation was focused primarily on being easy to read and simple enough that we had a chance to evaluate it and ensure that it exhibited what the semantics we intended, which is also why we have a complete set of unit tests in addition to the implementation of the system. But now that that is in place, the overhead can probably be reduced by going back to the code and performing optimizations and profiling it. And for future work, we, as I said, intend to could look into having a larger evaluation, performing optimizations of the code, and hopefully automating some of the now manual aspects of the implementation. As an example, the developers are now forced to choose between using the ref type for immutable data structures and Java ref for object references. That, based on some type checking, could probably be automated. Similarly, when you use the onCommit handle, you are expected to log refs before you use that onCommit, and that can hopefully be optimized as well. And that was it. Any questions? Well, it certainly, as you say, have some. If we could find another way to do these operations directly in Clojure, that would probably be more appropriate. And you could implement, if you need some sort of stop the behavior or blocking the thread behavior, you could re-implement your system using a concept Clojure has named agents that operate similar to actors, but has, so where the code is sent to the actor instead of messages. However, that would require that you restructure your code to utilize them. And so in that case, this is more, the implementation of side effects in the sim is more of a trade-off. You can use it sparingly if you can fit it inside your program. But if you have the luxury of restructuring the code and having a program and a concurrency mechanism that fits exactly to what you're doing, that would, of course, be more appropriate. One of the problems we've seen is that an alternative solution that has been used is to start adding Java or C# concurrency mechanisms such as semaphores and barriers to your program to compensate for software transaction memory in Clojure not having these concepts. So it then becomes a trade-off for us. Do we want to restructure and use agents, or do we want to start adding Java and C# code objects types to our system that doesn't really fit into our program, or do we have this compromise where we go a bit outside Clojure but then have at least a Lisp-like Clojure way of operating on this?
Event triggers insertion, verifying integrity and so forth. And I don't know what the software transaction is like in say Haskell or whatever, but it really feels like that these are the natural extensions to whenever you have a transaction period.
Yeah.
Is that relatively accurate?
I would say so, and there exists multiple different implementations of software transaction memory at the moment. Haskell, I don't know if they actually pioneered it as an implementation, but at least it's one of the more famous implementations. If I recall correctly, the paper is called Composable Transactions or something that way, where they proposed both the retry and Oils concept together with the original version of software transaction memory. A Scala implementation has included them as well, and a paper from, I think it was last year, called STMX also had these concepts. But for some reason, probably due to philosophical reasons, as we talked about just before, Clojure did not include them in their current implementation. So at least now they can.
Database at a small level.
What?
It's kind of like a database at a tiny level, right?
If you look at the implementation and have an understanding of multi-version concurrency from a database world, the implementation looks very much in that vein. You can definitely recognize aspects of a database implementation in this implementation of software transaction memory. I unfortunately haven't looked into Haskell's implementation to see how that works explicitly, but I wouldn't be surprised if similar concepts can be found.
More questions? Anybody hungry?